should be on. Yeah, okay, so we're on. Fine, let's see. Okay, last time we started talking about certain dynamical models. Okay, we have presented certain dynamical models showing or emphasizing the complexity of such models with the scope of understanding the purpose of the model reduction techniques. Okay. And we stopped at the single machine infinite bus, which is an electromechanical system typical for power grids. Okay, so this is a power generator that's connected, that's feeding the power into the grid, and it's connected through an infinite bus. Okay, to the rest of the world. That's the significance of the infinite bus. Okay, it's connected to the rest of the world, and this is the basic model. So that this means that the power grid is made of several such models. Okay, several meaning hundreds, thousands, hundreds of thousands, possibly millions of such systems interconnected. Okay, and as we have seen, as we saw last time, actually, this is not an easy model. This is a complicated model. Okay, it's a nonlinear model, as we can see here. Okay, and the nonlinearity as well as the dimension render this model as being a complex one, although it has only a few equations. Okay. Okay. Note that furthermore, this is a sort of differential algebraic system, in the sense that you've got a number of electrical dynamical equations, a couple of dynamical mechanical equations, and finally you've got two algebraic equations expressing the interconnection to the infinite bus. Okay. Okay. However, these algebraic equations still may contain, they can be turned into dynamical equations in this form. Okay. And finally, if we remember from last time, we saw that we've got 8 nonlinear equations that define such model. Okay. So the question of computing the equilibria, the question of discussing stability, transient stability, and all sorts of other issues regarding such model, they are difficult to discuss in this form. They are difficult to discuss in this form. Even if we have 8 equations, we've got the nonlinearities, we've got the couplings between the mechanical and the electrical states here. Okay, so that's pesky, and that's difficult to assess. And we were saying last time that that such models exhibit energies like this one. This is the energy function. This is the internal energy of such a system. Okay, and it's got if we pick the inputs and the outputs accordingly. Okay, we can prove that such a system is what is called dissipative. Okay, just like a resistor, dissipative. Its internal energy is dissipating. Okay, even if you supply energy to this guy, the internal energy is decreasing. That is because of the dissipation. Okay, and this property is very important. Usually, dissipation leads to the idea of stability or asymptotic stability. Okay. Like I said, this is a complex model, however difficult to use on large-scale interconnections. So imagine such a model interconnected in hundreds or thousands of connections, okay, for a power grid. Okay. So what physicists have tried to do is try to simplify, physicists and of course electrical engineers, they all tried to simplify the 7th or the 8th order model with a simple third order model. Of course, as usual, performing physical assumptions. For instance, they considered the fluxes to be non-dynamical, to be static or constant. So the dynamics, the equations of the dynamics of the fluxes are 0. Also, the steady state is considered to be just like a wire, a simple wire. There is no dynamics involved, although this is not true, but this is a physical assumption that there is no dynamics on the transmission line. So other sorts of fluxes are zero, and so on and so forth. This is what the physicists do, or the electrical engineers do. And then you end up with this third order equations, third order, sorry, system of equations, still nonlinear, if you can see. Okay, you've got the cosine here, so that makes it pretty nonlinear. You've got the KD here, which is also probably nonlinear, and so on. Performing certain manipulations in compact form, such a model can be written by these three equations below. Okay, x1 dot is x2, x2 dot is minus b1 sine, and so on and so forth. Okay, and so on and so forth. Where you easily identify the control, and the specific coefficients of such a model. Okay. So this is something which is currently used in power systems in industry. However, if this model is useful for certain analysis, it's still complicated once you interconnect it in a real power network, and you need to perform validation and so forth. So physicists and engineers once again started doing their magic in neglecting this and that and taking into account specific physical phenomena and trying to neglect wherever possible. So, for instance, neglecting the electromagnetic effects and keeping only the mechanical part of the generator as the important as the driving dynamics, if you want, in the slow dynamics or the driving dynamics of the power system, you end up with this second order equation of this form. J is inertia. If you look at this equation, this looks like a pendulum. This looks pretty much like a pendulum. Look at this term here. Look at this term here. So this is some sort of pendulum. Okay. Yeah, it looks like a forced pendulum-like model. It looks like a pendulum-like model. So we go back to the benchmark example. Okay. The nonlinearity is not necessarily sinusoidal, but it's periodic anyway. Okay, if you have these two parameters equal somehow, this term goes away, disappears, and then indeed you end up with an equation of this model equivalent or an approximating model of pendulum for the given system. Okay. For the given system. All right. So this is how people generally deal with simplifying physical models. The question now, there's two questions involved here. Question number one is this valid in the context of control engineering? Is this a good way to look at things if you do control analysis, synthesis, whatever? Is this a good way to do things? Is this how we should do it? This is the first question, because this is all physical stuff. The second question is then, as a consequence, can we find specific tools and models to perform model order reduction such that we end up with a low-order model that captures the essence of the given system, so that is useful for control theory? These are the questions we need to ask ourselves. And how do we respond to such a question? What's the answer to these questions? Is that we have to understand the basic idea of model order reduction. Okay. If you have a dynamical system, x dot is fxu. Okay, so it's a dynamical system. This is a general a dynamical system. This is not actually the basic idea, but it's actually the problem. We can call this a problem. This is the problem. Oh, dear. This is the problem of model order reduction. This is the problem of model order reduction. Okay. Um, Given a dynamical system with an initial condition and a specific output, okay, output being that guy which can be measured, okay, so you cannot measure the states, but you can certainly measure the output because that's why it's called an output, okay. The question is, can you find a system usually of the same type, okay? I mean, dynamical system, okay? You don't need to make up or cook up other types of objects. Yeah, the object should be of a similar type. Can you find the system psi dot in the new unknown psi? Psi dot is phi of psi and u, and chi. These are Greek letters, okay? Psi, phi, psi, chi is psi. So this is psi, and this is psi. Okay, this is with C and this is with a P. Psi, okay? Now look, X here, sorry, X here is in Rn, okay? Is in Rn, okay? And here you need to design a new system of the same type with this state, psi, this time function, psi, in Rn, okay? Such that the first condition is that the dimension of the new model, Ni, is much smaller, okay, is much lower than N, the dimension of the given system, the original dimension. And of course, the system, this is not 5, this is 3. I don't know what 5 is here. System 3. Okay, so this is all 3. System 3 preserves the properties or the structure of system 2. System 3 approximates system 2 within an error bound, so we need to look at modeling accuracy. Okay, accuracy is important, and we'll see to it. That's very important. And how to measure the accuracy of a model unless you measure the difference in the output response to a specific input. So you excite both the given system and its approximation with the same identical input signal, and you measure the outputs and you compare them. How do you compare them? You take the error of the you take the error between the two functions. So what I'm saying is, this is the original model, dimension n. I'm writing it like this. So this is input u, this is output y, and you've got the Ni approximation. This is an approximation, okay? This is an approximation. Okay? This is an approximation, okay? So you excite it with u, and here you measure psi. This u should be common. It's the same signal, okay? This is the same signal. So when is this an approximation? You need to measure the difference between the input, the real input y, and the computed approximated output psi. How do you measure this difference? Because you cannot measure like this.
Using the square error?
A norm. Using a norm. Square error is a norm of many norms, of many possible norms. Of course, using a norm, 2 norm, infinity norm, sometimes 1 norm, whatever norm is suitable for your application. Most of the times, the infinity, the 2 and the infinity norm are used, okay? Because these, they induce, such norm induces a norm on the error system, okay? So, for instance, y is t u, psi is t hat u. So this error here, so if you want to check, for instance, the 2 norm of the error of the output, this induces the infinity norm of t minus t hat. And if you want to check the maximum amplitude, I'm not sure if you guys remember the significance of such norms for signals. So Y and psi are signals. What is the true norm of a signal? Do you remember or do you know? What is this for a signal X? Signal X. What is this?
I don't know if I'm right, but I think the two norm is the energy.
Very good, energy.
And the infinity norm is the power.
No, it's not the power.
No.
No. Power is a different measure, and power is not even a norm, because it doesn't fulfill a norm. Mathematically, a norm has to satisfy 3 conditions simultaneously. Power is not satisfying one of them. Okay, the question is, no. So the infinity norm, this is the energy, and I'll write here. This is the maximal amplitude. Okay. Okay. This is the maximal amplitude. So true norm or infinity norm. So the energy of the error induces an infinity norm on the systems, and the maximum amplitude of the error signal, induces a 2 norm on the system. These are different from these, okay? So the infinity here and the infinity here are 2 different things, okay? They have kind of the same significance, however, they're not the same, okay? So infinity norm means maximum amplitude, okay? So this is, for instance, okay, the infinity norm of a signal. This is X, this is T, and this is the infinity norm of X, the maximum amplitude, the largest value that the signal can take in absolute value. Okay. Right. So if you remember, okay, I can write this as well. So this is the infinity norm is max. It's not max, it's supremum, if you remember from mathematics. Supremum of T of this guy. This is the infinity norm, okay? And the 2 norm of X, this is square root X transpose X, okay? Sort of, okay? So these are the measures that we take. We measure the norm of the signal of the error. Okay, we measure the norm of the signal of the error. Okay, and based on that, we compute other quantities. Okay, so the model order reduction problem is this one. Again, I'm repeating. Given a dynamical system of dimension n, which is large, okay, find a system. Another system in a different coordinate of dimension n, such that n is much smaller than n. We have preservation of properties or structure of the given system. So if the given system has a certain sparsity, is defined, or the equations that define the original model exhibit a specific sparsity, it would be nice to keep this sparsity in the reduced order model as well. I think this makes sense, doesn't it? Maybe some of you know what sparsity means. Or maybe you all know what sparsity is, okay? Sparsity is very important, especially nowadays in all these machine learning applications and all sorts of things. Then you'd like to check the accuracy of the approximation, measuring the norms I just showed you, okay? You would like to keep an eye on the accuracy of the approximation. You'd like the approximation to be as accurate as possible, okay? And of course, you'd like to have a reduced computational effort, okay? So the main reason why you would like to have an approximation of a given system is to reduce the computation effort, because the computational effort can be really huge, especially if you look at systems which are interconnected in high numbers. okay? So, or systems that exhibit a tremendously large number of interconnections, okay? So this is essentially the basic or the main philosophy of the problem of model reduction. We are going to try to understand, to give a solution to at the end of this course, okay? Because the rest of this course needs to make you understand what this object actually is, okay? What this object is, because probably you people have different backgrounds. I'm not sure if all of you followed the courses of our faculty. Are you all?
I'm not from this faculty.
Okay, have you followed any math courses or something, dynamics in some sense? Have you seen?
Yes. My background is in finance. I've graduated from finance and banking, and right now I'm at the master at the finance faculty that is dealing with econometrics, mathematical finance,
okay.
dynamical systems and things like that.
Okay, fine. My best friend in the Netherlands is at the Faculty of Economics and Business at the University of Groningen in the north of the Netherlands. And he is in the Department of Econometrics. He's a mathematician. He's my best friend and my mentor. Okay. And we work together quite a lot, but we work in control systems. But he also deals with this mathematical model. So maybe for you, it would be very nice if you could find a paper. You can, because this is a research master, okay?
Yes.
This is a research master program, so you need to show me research. So I would kindly ask you if you could look up in your references, in your literature, for an economics model that is complicated or that is complex, and maybe these methods will help you make a small approximation of such a model. I know that models from the economic field are very, very complicated and highly nonlinear.
Exactly.
Is this correct?
Yes, that's why I'm here.
That's why you're here. But here, of course, we'll show the methods for linear systems. So you linearize your economic model, and you'll apply these methods to linear. I also, if you're later interested, once this lecture is finished, if you're interested for nonlinear model reduction, I can show you, because that's what I'm working on. This is my research. So I can show you, but that's even more complicated.
I understand.
The idea is here to understand the principle of model reduction and the main methods, the main core methods to perform model reduction to have simple models. Okay, but
yes.
if you're from this field, and I'm happy you're from this field, this is new to me, and this is very useful for this class. I will kindly ask you to look for references, so look for some papers in your literature of economic models or of model reduction, which your people have already applied in economics, and compare to the ideas that we present here. For you, this could be your project for the exam as well. Select your own paper from your own field, show it to me, and then you make a report and present the results on model reduction for the dynamics of the economic model that shows up or emerges in your paper. We'll think about it. This is an idea I'm giving you, so think about it and contact me and show me if you have an idea, okay?
Yes.
But it would be interesting for me to see an example from economy or econometrics for this class. And we can teach it, you can teach it to me, we can talk to it together, you can present it in the lecture as well, I don't mind, because we have enough time. And we can discuss it and see if we can do something about it. Okay?
Perfect.
Maybe some simulations as well. We don't need to make theoretical results here. This is not because this is not PhD. This is just a master's class. But if you can make some simulation and have some practical insight into your problem, that will make me very happy, and I'm sure that it will make you happy as well.
Yes. Okay, I'm gonna search
Please do, because I'm sure, definitely. I mean, you can just start with exactly. You can start with Google or ask colleagues or ask professors in your faculty or yourself using Google and YouTube. I'm sure you'll find, only if you type model reduction economic model, I'm sure you'll find something, or approximation of the dynamics of an economic model. You definitely need to find something. And one other thing, I'm happy that you're here because I have a friend who is working also as software developer, but also in this field of risk management, and he's dealing with stochastic models and very complicated stuff. He knows a lot of mathematics, so he's not just a simple programmer, a simple key hitter. He's very happy, and he makes a lot of money, if you ask me.
Yes, in this field you need a very robust mathematical apparatus in order to be.
I agree.
To be relevant.
Yeah, the guy studied. The guy did his bachelor in Bremen, in Germany, and then did a master's in mechatronics in Hamburg. Imagine. And then he came here, and he's very well respected and well seen in his company somewhere in the Barbova Cărescu area, and they work for HSBC.
I understand. Yes, it's a very large bank.
But the guy is really. So I'm saying that this class could also be important for someone with this background and this purpose in his job. Okay.
Yeah.
Good.
Thank you.
This is good. Okay. I'm not sure why this. Oh yeah. Now so this is the general case with fx. Okay. Fx. This is complicated. Of course, there are methods for general dynamics described in this fashion with f of x. But we'd like to start from a particular case, which is very important for us, especially for us people in control, but also for people in other fields. In general, people like to look at linear models. The world of engineering and the world of dynamical system has developed a lot in the past in this field of linear models. Okay, for instance, for aircraft engineering. Okay, aviation, military aircraft, especially, and not only that, many fields, many fields, automotive industry as well. All the devices and the things that are automatic in your car, they start from mathematical models, from linear mathematical models, because they're easy to implement and to understand. And of course, people in control know it's easy then to apply a simple PID controller. For our friend who's not a control engineer, PID is a very popular control algorithm, which you can find as well you can find on the market anywhere. You can buy it, this solution. It's a little device designed in a certain fashion, which you need to tune to achieve what you like to have for your automated little system. Okay, so this is the PID control, and PID works with this linear dynamics. Okay, so in the from the general case of f of x, now we discuss the particular case when f of x is linear, is ax. Where A is a square matrix. A is a square constant matrix, and x is a vector or variable xi of t of dimension n. Okay, so x is x1t to xn t. This is x. Okay, and the matrix A is a big matrix. Okay, so given such a dynamical system, okay, and of course now the H, which used to be nonlinear, is also linear. C is a matrix as well. So we have the state in Rn, the input in Rm. We can have m inputs, and out we have p outputs. So this is a general case of multi-variable or multivariate dynamical linear systems with m inputs and p outputs. Find an object of type number 5. Find an object of type number 5 of dimension ni Ni is the Greek letter as well, such that the requirements are similar. Ni is much smaller than n, so the dimension of the reduced order model is much smaller than the dimension of the given dynamics. The approximant number 5 preserves the properties or the structure of number 4, and since we deal with matrices here, I come back to the idea of sparsity that needs to be preserved, or topology if we are talking about graph systems. Topology is important, okay? Also, you'd like 5 to be accurate, an accurate approximation of 4. So you look again at the error that I just showed you, and of course 5 is easy to compute. Now, where do you get systems of type 4? Yeah, where does 4 come from? This is the first question, and I'm going to talk about this because you people have different backgrounds. People in control have had classes of modeling and simulation, control engineering, where they have seen where 4 comes from. Other people, I don't know. So I'm just going to show you simple examples. Usually, dynamics means that a system can be described by a differential equation. Of course, we talk here about ordinary differential equations. We do not get here into details such as partial differential equations, because these are different objects and they are quite complicated, and they are beyond the scope of this class. Furthermore, there is no lecture of partial differential equations in this in our faculty as well, except for a few hours in a course of mathematics. Okay, so where does 4 come from? So you get, for instance, you get this equation: y double dot plus ay dot plus by equals u. So this y of t, okay, is something you need to calculate. Y of t can be displacement for mechanical system. It can be a current or a voltage in electrical system. It can be the exchange rate, but that's a discrete. Okay, this is a bit far-fetched. Such a system for the exchange rate should be a discrete time system. This is a continuous time, but okay, the exchange rate, and so on and so forth. So such equation defines or spans a large class of systems. A large class of systems. This is just an example. How do you turn this into the ABCD? You make the notation. So this is a second order equation. A second order equation. So this is difficult to compute like this. Okay, or it can be computed because it's a linear equation. But again, it's a bit difficult. So to make it easier to turn it into a first order equation, what you do is you write x1 equals y. X1 equals y. Okay, then you get y dot. I told you that dot is d to dt. This is the time differentiation operator. Okay, we use this notation in dynamics. Y dot. Okay, so y dot being dy dt is x2, which means that y double dot, which is d2y to dt2, which is d to dt, okay, from dy to dt, okay. So I'm just showing how the differentiation works here, okay, how differentiation works here. This is x2. No, this is x2 dot, sorry. This is x2 dot, and x2 dot now comes from this equation, so is minus a. It's minus a. or let's put it like this, minus bx1 minus ax2 plus u. Do you see that? This is x2 and this is x1, okay? According to the notation we have just made. Okay, so now when you write your equation, so this equation, let's call it number 1. Equation number 1 is equivalent to a system of two first-order differential equations. x1 dot is x2, and x2 dot is minus b x1 minus a x2 plus u. Okay. Still, this is not in the matrix form that we'd like to. But we make the following notation. We call x the vector x1, x2, which is in R2. Okay. Then x dot is x1 dot, x2 dot. Okay. x1 dot, x2 dot. And this is, you can write it first like this, x2, and then minus b x1 minus a x2. Okay, and separately, you can make this separate, plus 0 u. Okay, so these are vectors. Okay, these are R2 vectors. Okay. Now the question is, can you write this guy into ax? Can you write this guy into bu? You can probably do that. Okay, so this is a matrix times x1, x2, plus another matrix times u. And for this matrix, we have 0x1 plus 1 x2. You see? Yeah. Minus b x1 minus a x2. Can you see that? And here you have 0, 1. And now you've got your A and your B matrix. Of course, the matrix C, if you want to make the output, the matrix C times X, you choose your C. Yeah? Keep in mind that if you have only one output, your matrix C is a line matrix. Okay? With two elements. I don't know, you can take 0, 1, for instance, or whatever. This is just a choice. This is just a choice. Okay? So is it clear where the A, B can come from and C? Is this clear to you?
Yes.
Okie dokie. So this is where you get these guys, but these guys can be really huge. In our example, the things are really small. Okay, and it's not an issue. But in these guys, this n can be really, really huge, and m can be also big, and p can be also big. But we do not touch m and p. The number of inputs and outputs is the same. Okay. So you want to design this guy. How do you design this number 5 to approximate number 4? This is the main question. Okay. And we have here, for the basic idea of model order reduction, we present a diagram. How the procedure goes. Okay. This is a diagram about how things have to be done to get to the bottom of designing F, G, and H as the approximations of A, B, and C. Okay. We've got an original model. Okay, so you get the A, B, and C from some modeling. Mechanical, electromechanical, electrical, electronic, economic, and just talked about this with our friend here. You perform model order reduction, you get a reduced order model, yeah, reduced order model. You replace the original model with a reduced order model, okay? So you integrate the reduced model with the rest. This is an idea from electrical engineering, okay? You have many components. You make a reduced model of the component. You put it back. You put it back in your circuit, or integrate it into the process, and then you use this reduced order model to perform specific control and specific control design and analysis, okay, to perform specific stuff. Now, more concretely, let's put our hands on on things, and the main question here is, how do you build the reduced order matrices F, G, and H? How do you do that? The main problem is you need to build these matrices such that the constraints of the model reduction problem are met. So essentially, you need to fulfill these things. Now, another question is, how do you select Ni? Well, that's a bit tricky, because you do not have, or at least I do not have for the moment, a precise, specific, or systematic answer to this question. I cannot exactly tell you how to pick Ni. However, you do that from engineering practice or from economic practice, and you know, or you merely do trial and error until you get your desired results. The solution to the problem is to build projections. The projections are the solution to this problem. Okay, so you would like to find a subspace that includes the original X, and you'd like to project this X to the subspace to approximate it. Of course, the subspace is of lower dimension. So what you do is you write this projection. To build the projection, you write this relation. Yeah, Xi is of lower dimension. Xi is of dimension n. Ni, sorry. X is of dimension n. So V is R n Ni. So this is a tall matrix. V is a tall matrix. Okay. This is the original model, and this is the approximant. You substitute X with V Xi. So if you substitute X with V Xi, X dot, so this means that X dot is V Xi dot, because the V is a constant matrix. So the only quantities the only functions that depend on time are X and Xi. So they are subject to the differentiation. So you differentiate X. So V Xi dot is A V Xi plus BU, and the output is C V Xi. Now, how do you finish and you get everything in Xi here? You employ the so-called Petrov-Galerkin projection. This is what people in model order reduction do. So you build another matrix W such that W transpose V is the identity. Okay. W transposed is a wide matrix, so W is again tall. Okay, so W is also of dimension n times Ni, because then W transposed is of dimension Ni times n. So when you multiply them, they can be multiplied, because W transposed has n columns, V has n lines, so they can be multiplied. Right? So what is the projection? The projection essentially is the matrix P, and this is V W transpose. This is an n-dimensional matrix. Yeah, this is R n times n. Okay, and usually to be a projection, that means that P squared needs to be P. Okay, P squared equals to P. So if you do P squared, that is V W transpose V W transpose, you notice that the product W transpose V in the middle of this matrix, this multiplication is the identity. So you end up with V W transpose, which is exactly the definition of P. So indeed, P is a projection matrix because P squared equals P. Hence, you apply W transposed on this guy, on the first equation actually. You apply W transpose on the first equation, okay, and you end up with the final model. So this is F, this is G, and this is H, and they're all of smaller dimension. F is dimension Ni, G is dimension Ni M, H is dimension P or Ni, P times Ni. Okay, and this is the reduced order model that you obtain. The question is, how do you build the projection? Because you need to satisfy the model reduction problem conditions, constraints. So the trick here is in algorithms designed to build such projections. Okay, this is the main trick. You use projections to do the model order reduction. The key lies within the way or the how you design these projections. How you design these projections. In conclusion, the whole thing boils down to the question: how do you build W and V for these large-scale and complex systems? How do you do that? This is the question we need to answer throughout this lecture. Okay, and we have here two classes of methods, the main classes of methods. Of course, they have a lot of subclasses and a lot of variants. Okay. However, before going to the main methods of doing model order reduction, we actually need some systems theory recap. Okay, and since we have friends here of different backgrounds, I think this is more than called for. You agree, right? That we need to start discussing in detail about dynamical systems. Do people agree? Even for control engineering people, I'm sure they do not remember all the ideas about controllability, gradients, and all these things of a dynamical system. So I think the next few lectures, quite a number of them, are dedicated to fixing the class of systems ABC and what we can do with it. Okay. So we'll recall all of these ingredients over these lectures. Do you agree with me?
Yes.
Yes, sure.
Okay. On the other hand, I discovered something very, very interesting. Before I go any further, I'd like to show you something. I'm trying to connect myself to Moodle. I also invite you to do the same, to connect to Moodle. Okay, because Moodle contains a lot of information, and I'm uploading. There is already uploaded quite a lot of information. Oh, this is a different lecture. Sorry. No, this is not the Moodle dashboard. Okay. So this is our lecture. This is our lecture. There is this model order reduction portal. As you can see, do you see the link here? I'm talking about this link. You can see my screen, right?
Yes.
Mm-hmm. Okay. So you see the link here. Let's open this link. Modelreduction.com. This is made by one of the famous guys in this field, Professor Peter Benner from Magdeburg in Germany. He is one of the pioneers of model order reduction. Look on this very nice picture here that gives a clear idea of what we're going to discuss. So you get models. For instance, you use finite element methods. You get systems of n ordinary differential equations. Okay, you do model order reduction. You get a reduced order model, and here below you have applications that you can see, and then you do what you can do with your reduced order model. Okay, so let's see what they say here. So the goal of this site is to promote the use of model reduction in industry. Okay, And I'm going to add here for our friend and economy as well, or econometry as well, to get compact models directly from finite element models. Now, what is this finite element? This because usually most of the complicated physical phenomena and processes or industrial processes nowadays come from partial differential equations that have dynamics both in space and time. So these are partial differential equations. You know that these usually cannot be solved analytically unless they are very simple. Okay, so there is a limited class of partial differential equations that can be solved analytically. But in general, what people do is use numerical methods such as finite element methods to approximate the partial differential equation with large sets of ordinary differential equations. These methods are called finite element. What do they actually do? They discretize, oh, I cannot write here. They discretize the space into grids, just like the little squares that you see here. Okay, just like this grid that you see on this screen.
Yeah, mesh, right?
A mesh, exactly, mesh or grid. So you discretize the space, and in each point of the grid or the mesh, you write a set of differential equations. Okay, that's in time, differential equations in time. So you discretize the space and keep the time variation, the time dynamics. Okay. This is what finite element methods do, and this is a huge chapter in systems defined by partial differential equations. So model reduction makes the links between ANSYS. ANSYS is one of the big softwares that is able to perform finite element methods. People in computational fluid dynamics use this, for instance, in aircraft in engineering. Okay. Okay, the guy says here the content is biased towards my personal work. The guy has a lot of work, so you need not worry about that. So this is very interesting. So I invite you to research this website and look into it. And we're going to look into it on a lot of things. For instance, we have here model reduction. I don't know what this is. See, this is how you perform model reduction. So here it's showing you exactly the paradigm I have just presented to you. The projection that you build, this is X, the original state, and Z is the reduced order state. So model reduction or model order reduction is a mathematical theory to find low-dimensional approximations for a system of ordinary differential equations, it says here. Okay, the main idea is that a highly dimensional state vector actually belongs to a low-dimensional subspace as shown in figure 1. Okay, like this. So this is the V I just showed you a few minutes ago. Okay, I showed you a few minutes ago. Provided that the low-dimensional subspace is known, of course it's known because that's where you want to project your dynamics. The ODEs can be projected onto it. Okay, so this is shown in this figure. This is shown in this figure. Okay, so look, you substitute here X with VZ. Exactly what we did a few minutes ago. It's exactly the same thing. And now look, the big squares become small squares. So this is reduced. This is reduced. Okay. Now I'm not sure why I'm seeing these stupid commercials, but okay, that's life. The goal of the mathematical theory is to find such a low-dimensional subspace. Available methods for model reduction are classified as follows. Linear describes the reduction for linear, and this is what we're going to study. Second-order systems, for instance, for mechanical systems. Parametric, because the A, B, C matrices can also depend on parameters. In our case, we take the simplest case with A, B, C constant matrices. Nonlinear, weakly nonlinear, restricted to quadratic or cubic terms, but also nonlinear, which I have been working on in my research for the past 10, 12 years. Okay. Discuss the model reduction for a general nonlinear system of ODEs. Okay. And you have here the books, which are very nice. Okay, and you have special issue on some magazine. Oh, look here. Andras Varga is an editor. He's Romanian. Andras Varga. He used to be in Germany. I don't remember exactly where, but he used to be in Germany. So this is a very nice website, which we are going to study closer to the end of this lecture. If you want to take a peek before we reach our moment to describe these methods, please be my guests. We are going to use this website in our studies, okay? I think it's very interesting, and it's exactly the essence of this lecture, okay? All right. Okay. Now, where was we? Okay. Let's just wait for a second because I have to. Let's take a short 5-minute break until I upload the next set of slides. Okay. I need to upload the next set of slides. So you can also take a 5-minute break if you like. We'll get back here in a few minutes. Okay, we'll be back here in a few minutes. Okay, I'm back. Please confirm you're still here, please.
I'm still here.
Okay, fine.
Yeah, I'm here too.
Okay, good. Let's carry on. Okay, so let's recap some basic properties of state space systems. Okay, so we start with some basic characterization of linear systems. LTI models. LTI means linear. Sorry. LTI means linear time invariant. Okay, so that means that the matrices ABC, parameter matrices, are constant matrices. They do not depend on time. Okay. These models can have attached a transfer function matrix applying the Laplace transform, as we'll see. They also have evolutions of the state. They can exhibit stability, and this is very important. And we'll see the conditions under which a state space system is stable. And of course, they can have a steady state response, and this is important. Okay. The steady state response of a linear system is important. So these are the notions we're going to play with in the beginning. Okay, so again, the class of systems we are trying to study in this state space context are linear, they are time invariant, they are finite dimensional, so they have a finite set of poles. Okay, we'll see we'll recall what poles are soon. They can be multi-input, multi-output, so they can have more inputs and more outputs. This is MIMO, okay? The particular case is single input, single output, that's CISO, or single input, multiple output, that's CIMO, or multiple input, single output, that's MISO or MISO. So this is the class of systems that we are going to use. What exactly is linear? So linear means that if you have a system like this, an input-output, so the output Y is the operator T of input. Linear means that T of alpha U1 plus beta U2, okay, is alpha T U1 plus beta T U2. This is Y1 plus Y2. So this is what linear means. Okay, so this is a linear operator, and the way we define these systems in the dynamical constant, they still observe this property. Okay, so they are linear. Definition. A linear time invariant dynamical system is a four-tuple of constant matrices A, B, C, D, where A is a square matrix of dimension n, B is a matrix of dimension nm, and C is a matrix of dimension pn, and D is a matrix of dimension pm, so P outputs, M inputs. So a linear dynamical system, I would say here, with M inputs and P outputs, is this guy with the following significance. The first matrix is Ax dot of T is Ax plus Bu, so these are the dynamical equations, the ordinary differential equations set up in this matrix form. Okay, so there are n first order differential equations with n unknowns. Okay, and they are written in this matrix form here. And we have also the output equation, which is an algebraic equation. Y is Cx plus du, with the initial condition xt naught is x naught, generally defined as x naught. Okay, so this is dynamical. This is the definition of a dynamical system we just showed on the previous in the previous hour, we showed how this can be, where this may come from. Okay, that's not the only place where they come from, but that's one of the areas where where these that exhibit this kind of models. U is the input. It belongs to the space of input functions or input signals, because they're usually signals, step, harmonic, and so on. YT is the output. So this is what we measure. Okay, usually what we measure is included in the output, and Y, capital italic Y, is the space of output functions or of output signals. And XT is the so-called state vector, or the vector of states of the system, and it belongs to an X, which is state space. Usually, for simplicity, we are going to consider Rn as our state space. Okay. So a few remarks are in order at this moment, so we can clearly understand the object we deal with. Okay. So the dynamical system model above describes, they say here in a condensed matrix form, a system of n differential equations with n unknowns. The unknowns of the differential equations are the states, while the outputs are a linear combination of the states, and the outputs are usually measured. Okay, so the outputs are a combination of states and inputs. Most of the time, we'll take the case of the combination of states, considering the D matrix 0, which is usually the case in real life. The system is automatically linear, time invariant, finite dimensional, and causal. Okay, so it's a cause and effect. I'm not going to get into details. This is a question of mathematics. Causal means that is zero. All the time functions are zero before zero. Okay, it's linear. It's time invariant because the ABCD matrices are constant matrices, and is finite dimensional. Okay, because the eigenvalues of A is a finite set. Okay, so finite dimensional. The eigenvalue set of A is a finite set. Okay. Do you remember what eigenvalues are? So let's just make a recollection. If we have, so consider the matrix A of dimension n. Okay, lambda is an eigenvalue. Of A. Okay, eigenvalue. Eigen is own value. Valoare proprie în românește, da? Is an eigenvalue of A if and only if there exists a vector V in Rn, V non-zero, such that AV equals lambda V. V is the eigenvector of the eigenvalue lambda. Okay, do you remember these notions?
Yes.
Yes.
Okay, fine. Now I'm going to remind you the characterization of eigenvalues. Okay, so the mathematics says that lambda. Okay, and the set of eigenvalues is denoted by sigma A or lambda A. There are several notations. So lambda is an eigenvalue of A if and only if determinant of the matrix lambda I minus A is 0. Okay. So lambda is the root of the polynomial that lambda I minus a. This is a polynomial function, okay? This is a polynomial function. Just a reminder, okay? Because we are talking about finite dimensions, okay? So if the spectrum of the matrix A is finite, then the system is called finite dimension, okay? There are systems that can have an infinite number of eigenvalues, even if they are deterministic. And I remind here, especially for the people in control, time delay systems or deadbeat systems. They are infinite dimensional systems. Okay. All right. Good. Okay. So since the object we describe here is time invariant, we can always take the t0 from the initial condition to be 0. Okay, and the initial condition can always be rewritten as x0 is x0. Okay. Now we can see this system as an input-output system in which the state actually plays a coupling role. It plays a coupling role. Okay. And the system is completely defined by the four matrices A, B, C, D. And here, of course, we consider piecewise continuous input functions, implying that both the state and the output are continuous as well. Okay. Of course, now since we deal with a set of differential equations, we have to check the solution of the set of differential equations. This is what we are interested in. Of course, because sometimes it's difficult to write the solution, it's nice to have qualitative behaviors, and that's what we are going to investigate. We also have an input-output behavior, which we are going to emphasize, okay, because the input-output behavior is also relevant for the final goal of this lecture, that is to perform model order reduction, okay? So the first equation of the system, this x dot is ax plus bu with the initial condition x of 0 is x naught, is in fact a system of n ordinary differential equations with n unknowns having a unique solution because of its special form, when the initial state and the input are known and fixed. Okay. What is the unique solution of this system? This is the first main question. So you have the equation x dot is ax plus bu. You remember last time we discussed the solution of the equation of the scalar equation x dot is ax plus bu. Is that true? Did we discuss this last time? I remember that we talked about this last time. Now, the same ideas do apply to this simple first order differential equation. So you look at this as a differential equation, but in a matrix form. So the x and the a, they are no longer scalar functions, but they're matrices. Okay, so that means that the solution and the initial condition here, the solution of x dot is ax plus bu is xt is x general of t plus x particular of t. This is from the differential equations theory. Is the general solution plus the particular solution. This is the solution to the Cauchy problem of solving a differential equation. This is a first order equation. Okay, xg is the general solution. Of x dot is ax plus bu. That is edest. Xg is the solution of the system x dot equals ax. So when b is 0. xg is the solution of the so-called homogeneous equation. X dot is ax. This is the homogeneous equation. Associated to x dot is ax plus bu. Okay? So what is the general solution of this guy? Recall. For x dot is ax, so in the scalar case, what is the solution of this? X is the initial condition times the exponential, e to the power at. Correct? Is it true or not?
Yes.
Okay, so what do you think, extrapolating, what do you think the solution of this guy is? Xg is what?
It's x0, yes, or e to the power of 80.
Very good. Where this is the matrix exponential. This is the matrix exponential. E to the power at is defined through the Taylor series expansion. I plus at plus a squared, t squared, and so on. Is this a solution of the equation? Let's see. Xg dot is d to dt from x0 e to the power at. So this is x0 times d to dt e to the power at. Now what's the derivative of this guy? Let's take the derivative of this guy. Okay? What is the derivative of this guy? I dot is what? D to dt from I is?
0.
0. D to dt from at?
A.
Then d to dt from a squared t squared? Oh, here you have 1 over 2. Yeah. Is 2 times 1 over 2 a t. True? A squared t, sorry. A squared t. True? And so on. We can extract a as a common factor to the left. So this is a identity plus at plus so on. So this is what? A times e to the power at. We substitute back here. So this is x0 times a times e to the power at. Oh, but this is wrong here, because you cannot write this here. This is wrong. Sorry, because the multiplication is not correct. This is a matrix, okay? So is EAT times x0. Okay? We have to be careful when we talk about matrices, because the multiplication, the order of multiplication is important. Okay? So x0 is to the right of this guy. X0 is to the right of this guy. Yes, but okay. So now multiplication is associative, so we can delete the brackets here and move the brackets here. And what is this? This is xg. True? So indeed, xg is the solution of this equation. Yeah? Okay, let's go back to the slides. So the unique solution of this equation, is it clear what we have just done?
For me, it is.
Okay, this is first year mathematics. Okay, first year differential equations math. So the unique solution of this guy is x of t, which is a function phi, which depends on time, the initial condition, and the input. This is the general solution or the free evolution of the system. We use here the Romanian terminology, liber and forțat. This is the free evolution of the system, plus the particular solution. So this is the xp, this integral term. This is the particular solution. This is the particular solution. Okay. So you have the free evolution plus the forced evolution. Forced because it depends explicitly on the input u, which is an external influence on the equation. So this is the general solution of such an equation. This is the general solution of such an equation. So now we need to investigate its properties. Okay? We need to investigate its properties. This function that defines the solution, this function phi that defines the solution, which is defined on r, this is from the time. So this is the time. This is the state vector. The state vector is called the state transition function. That's how we call it, state transition function. Okay, so notice that, okay, now I'm talking more the superposition principle, where the effects on the system, the linearity, the property I showed in the beginning. This is so this additive decomposition XL plus XF emphasizes the linearity property. Okay, so this is a one-to-one with the fact that the system is linear. The fact that the system is linear. Okay, due to the initial condition x naught, the free evolution due to the input. So the free evolution and the forced evolution can be easily added together, and then you get the final solution. But this is due to the linearity of the equation and the linearity of the system. Okay. The matrix E exponential of AT is called the state transition matrix. Okay. So with this notation, the solution of the differential equation can be expressed in equation number 2. Okay. You agree? Is it clear until now?
Yes.
Yes, it is.
Yes.
Okay. Yeah, it makes sense. Okay. So this is the general solution. Now we have to look into the things. Now the first question that comes to mind, okay, and how do you compute this exponential? Because you can imagine you're not going to use the Taylor series expansion for let's say real-time applications or computation. Okay. So how do we compute the solution? What does it mean, and how can we compute the matrix exponential e to the power at? This is the main question here. By definition, so now I'm actually repeating what I've just told you about the matrix exponential. It's defined based on the Taylor series expansion of the classic scalar function e to the power x. So by definition, if e to the power x is defined by the Taylor series expansion in this fashion, 1 plus x plus 1 over 2x squared plus so on and so forth. In the matrix case, you merely substitute x with at. So now instead of 1, of course, because we are talking about matrices, the 1 becomes the identity matrix. So in plus at plus half at squared plus so on and so forth. Okay. The computation of this matrix is essentially based on the so-called Jordan canonical form of the matrix A. Do you people remember what the Jordan canonical form of matrix is? Because both economists and engineers should know about this.
Something like it had blocks of matrices
blocks of
its,
matrices on the diagonal. Block diagonal matrices where each block belongs to an eigenvalue of a certain multiplicity. Okay? Okay.
Yeah, we did stuff like that
in the first year.
Yeah.
Linear
in the last year.
Last year.
With Professor Fluter.
Ah, Christy showed you these things. Okay.
Yeah.
Because Christy also works. Christy is also working with these things, so this is a good refreshment. Okay. State transition matrix and response. Okay. We also have a so-called time reversibility, which is specific or peculiar to linear systems, in the sense that if you can compute a state from the initial condition, you can always recover the initial condition from any state. This is again, so if you have a trajectory, okay, this is the initial condition, and you can compute the trajectory to get to this final point. If you go this way, for linear systems, you can always go backwards. Note that this is not true for nonlinear systems, for instance, for the pendulum, if you think about it. This is not true. Okay, so this is true only for linear systems. Okay, so the initial state or the initial condition can always be recovered from any state trajectory that you compute. Okay, so if you know the current state and the input generating it, you can always get back to the initial condition. Okay. Now, what is the output of the system? The output is an immediate consequence. You multiply the x by the solution x of the differential equation x dot is ax plus bu. You multiply with c, and then you get y. The output is c exponential of at times the initial condition x0 plus the forced output. So this is the free output plus the forced output, which is the integral. And the c goes into the integral because c is a constant matrix. So if you have a free evolution plus a forced evolution, you also have a free output, a free output plus a forced output. Okay, you have both. Okay. All right. Now, if you let t of t be this c e to the power at b, and you define this t index c of t, then or you can write tc as t times the Heaviside signal, okay, the step function. With this notation, you can always write that the output y is c phi of t x0. This is the free output. So this is the free component. And this is the forced component, which is this guy. Okay? So if the initial condition is 0, then the output is only given by the forced component. Only given by the forced, which is the case when we study linear systems, because we are interested both in the free evolution, but mostly in the forced evolution. Okay, so this we express the output as the echo through the causal TC function when the initial condition is set to 0. So under 0 initial condition, the dynamical system can be expressed as a convolution system. Do you people know about convolutions, or do you remember about convolution systems? Hmm? Do you remember about convolution? Do you have any recollection of convolution?
When I think of convolution, I think of that integral. This is all.
The integral, but you also think about, for instance,
that's a summation, right?
Yeah, okay, that's discrete convolution. Because you're an economist, you think of discrete systems. a summation for discrete time, and an integral for continuous time. The convolution is the operation that shows us the response of everything with respect to anything.
But basically, it stands for like a function of another function, right?
No, it's a convolution. It's not function composition.
No, I know, but like an intuitive meaning.
No, it's actually no. The intuitive idea of convolution is the echo. The response y of t, if you have a convolution, y of t is the convolution of two signals, ht, convolution ut. Y is the echo of u through h. Echo, like you shout in a room, okay? You shout somewhere. You go to the mountains and you shout. The u is your shouting, is your voice. The h are the mountains and the configuration of the rocks. And the echo that you hear, is the response. Do you follow me?
Yes.
Yeah, this is the response. So essentially, any output y, that's what it's saying here. Any output y of the system is any forced output is the convolution, is the echo of a signal u through the system described by this function Tc or by the four matrices A, B, C, D. If you how can I express this? If you push a ball on a table, okay, you have a ball resting on a table. If you push it, that you give an impulse, okay? The ball is going to move, okay? So the movement of the ball is the echo of your pushing of the ball on the table, okay? So the ball and the table are the system. The pushing is the signal, is the impulse signal, and the movement of the ball on the table is the echo or the response of your pushing of the ball. Is this somewhat clear?
Yes, it is.
Yes.
Okay. So if you have, maybe you have some examples for later, but try this in MATLAB if you do not believe me. Take any system, the easiest system. Use the state space function, okay? SS. Take random matrices like you have the building, or you have the CD player, or you have the card pendulum. Use the SS function to build your system. State space, yeah? SS of A, B, C, D is computing this system. AX plus BU equals CX plus DU, okay? And you take the impulse. Imagine you give an impulse. Yeah, this is your system. And plot impulse of sys. That's the echo of an impulse through the system. Okay? And have a look at the plot. Have a look at the plot, okay? Right? So this is how actually what the system actually defines is a convolution. By the way, the convolution operator is linear. Okay? Of course, it's linear. Okay. So if you have now m equal to p equal to 1, then you get the simple single input, single output case, where you have the causal response of the system when the input is a Dirac function, because the Dirac is a neutral element with respect to the convolution operation. Okay, so that means that h times Dirac function is Dirac times h is h itself. This is a neutral element with respect to convolution. Okay, so your ABCD system is described uniquely via the ABCD matrices, and also equivalently and as well uniquely through this matrix TC of time. TC of time. But from an input-output perspective, because now we want to prove the input, we want to emphasize the input-output behavior, We can also build a transform matrix. We can also build a transform matrix, and for this, to compute the transform matrix, we need to compute the Laplace transform. We are going to use transform matrices. The Laplace transform of a signal x of t. Does anyone know or remember what Laplace is? Our friend from the economy, have you used Laplace transform ever?
I know the concept, but I'm not.
You can look it up on Google.
Yes.
Laplace transform. It uses tables. Okay.
Mm-hmm.
It transforms the signal from the time domain to the abstract S domain in a complex function. And this is integral from 0 to infinity xt e to the power minus st dt. Okay, this is the formula. This is how it's an integral transformation, just like Fourier. Maybe you've heard about Fourier transform.
Yes, of course.
Or signals. It's similar. It's more general than Fourier. Fourier is on the imaginary axis. It's only j omega. Yeah, in Fourier you have x of j omega. Whereas here you use the general complex variable s. Okay, and the Laplace transform has properties. The Laplace transform has properties, and you can find this on a table. You just look it up on Google, and you'll find millions of tables with Laplace properties. Okay, so we are going to apply the Laplace on the AX plus BU. Laplace has a property that Laplace of x dot of t is s times xs minus the initial condition x0. This is something you can find on the tables. Okay, so applying Laplace transform on the AX plus BU yields sxs minus x0. Yeah, so we have here Laplace on AX plus BU equal x dot. We take Laplace of this equal x dot. Laplace with initial condition 0. Okay, here it's just taking Laplace, no initial condition 0. Okay. So on the left you get sxs minus x0. This is Laplace of x dot I just showed. On the right hand side we get ax plus bu. And for y, since it's an algebraic equation, it's clear. Okay. Since the matrix Si minus A is almost everywhere, that's what this thing indicates. It's almost everywhere invertible except its own eigenvalues. But that's a finite number of points. It's a finite number of points because we said these are finite dimensional systems. You can easily rewrite that Sx, because you take this guy to the left, is Si minus A to the power minus 1 times x0, x0, plus Si minus A to the power minus 1 Bu. Okay, so again, you have x dot is Ax plus Bu. You take the Laplace, you have S xs minus x0 from this property is axs plus bus, b not of u but b times us. And one other thing which is very important, Laplace of the convolution, that's why we use the Laplace transform. Laplace of the convolution is the product of Laplace transforms. This is the very important property. Okay, so you get sxs minus axs equals x0 plus bus. Can you follow me? I think I haven't lost you, have I?
No, it's clear.
It's not difficult. Now we take. Sorry? Can you repeat, please? Someone was saying something and I misheard. Can you please repeat?
Can you repeat the question?
I was asking, you were saying something. I was asking you if you are following me, or am I going too fast?
Yes.
These are simple things you should kind of be familiar with. This is kind of prerequisites for this class. So x of s now is a common factor to the right. So then you get s I. You need identity here because s is a scalar and x is a matrix. Minus a times xs is x naught plus bus. And this is, since this is invertible almost everywhere, like we just heard, then you get that xs is si minus a inverse x naught plus si minus a inverse bus. Okay? So we kind of re-explained this relation here, okay? This result, okay? Now, one other thing, just keep in mind that Laplace of the exponential is si minus a to the power inverse. This is called resolvent matrix, anyway. And also, phi is Laplace inverse because the Laplace transform admits an inverse, okay? Moreover, phi of s can be can admit this series expansion. So phi of s is si minus a inverse. And how do you compute an inverse? Is si minus a adjoint over determinant of si minus a. This is something you know from the 11th grade, okay? So m to the power inverse is 1 over det m adjoint. Do you remember that? This is from the 11th grade. This is from high school. Well, Romanian anyway.
Yes.
Okay. So this determinant is the characteristic and minimal polynomial of A. And then the Laplace transform gets this way. So the output y of s is, this comes from the free output, and this is the forced output. And this here is the transfer function. This here is the transfer function, h of s, t of s, whatever we call it. This is the transfer function, or the transfer matrix. So the transfer matrix is the Laplace of the TCT impulse response, and this is the transfer function. And we also use this notation. This is a notation, this is not a matrix. Okay? And we finally get this relation. So from ABCD, we can always go back and forth. To an input-output representation. I think this is enough information recollection for today. Do you agree or do you want more?
I agree.
You agree. The rest of you? The others? How about the others?
I agree as well.
You agree as well. It's a lot of information. You can play with this. You can read about it. Those of you from control engineering can go back to the control systems class from the second year and recall these things. Please go to MATLAB, take the building, take the CD player, take the card pendulum, generate using the SS function the state space system, okay? And then use the function SS to TF, so from state space to transfer function, also TF to SS, okay? And see what happens. Last time I was asking you to take random matrices and generate of large dimension and see how they generate these things. Also try that, okay? Please try that. And also go to the model reduction website and also to the book of Antulas for further details. Do we have a deal?
Yes.
Yes.
Okay.
All right. Have you got any questions, please? Any questions?
Teacher?
Yes, please.
This presentation about state space system will be uploaded on Moodle?
Certainly, and you can always access it here in the notebook, because the notebook stays forever. Can you repeat, please, because you have background noise and I can't hear you.
I asked about this presentation.
Yeah, I told you. You can find it both in this notebook and on Moodle.
Okay.
Yeah, it's here because this notebook. So please remember, this notebook is always available to you with my notes on it. This is always available to you. Okay, constantly throughout this lecture. You can go back and forth from page to page. Please install and use OneNote, Microsoft OneNote, please. Yes? All right, and you can always access through Teams and through your Moodle account, you can always access this guy. Okay? Furthermore, everything is going to be uploaded on Moodle as well, so everything will be found on Moodle. Okay? Okay. Any other questions, please? Any other questions, please?
I don't have other questions.
Fine. All right. Okay, I'm going to leave this call open because it's going to be open until 8 o'clock. If you have questions or you need to talk to me, please say something or write on the chat, and I can, when I see the message, I can respond to you. Okay, so the call is open until 8 o'clock. Okay.
Okay, thank you.
Okay. Thank you.
Thank you as well.
Thank you very much. Thank you.
The recording is stopped now. Okay, so if